Okay, today's topic is taking a look at the ambiguous case of the sine law. Now, ambiguous means information given to us can be taken in more than one way, and that's exactly what's happening here. Depending on how information about a triangle is conveyed to you, it could have more than one implication. So anyway, let's break this one down here. Ambiguous case right there in the micro concepts. First off, it's important to note in your calculator, if you were to take the ratio root 3 over 2, and do the inverse sine, that there's actually two angles that have it. Now the calculator will only ever report one of them. It'll tell us that it's a 60-degree angle because the calculator is looking for the cheap and easy answer, the one that's nearest zero or the smallest answer. Even though 120 is, the sine of 120 is also root 3 over 2, and you can check that on your calculator if you want to. It's absolutely true. Now, why is this a problem? Well, it's not a problem for us. Why is this an issue that we need to consider? It's because sometimes when we use the sine rule, we use it to find angles. And if we're finding angles, if the angle was obtuse, our calculator is not able to tell us about that. So we need to know whether or not it was a possibility or not. And if it was a possibility, what is that possible angle? I'm going to take a look here. I'm going to draw a hypothetical triangle, and I'm going to show you exactly how we can run into this problem. Now I'm going to take a long straight line, stick it horizontally there, and I'm going to draw an angle here at about 30 degrees, just have another line going off into the distance there. I'm going to get my ruler out, and I'm going to measure off 6 centimeters. No, I'm going to measure off 10 centimeters here. There it is. Now what I'm going to do is I'm going to make a side A. Remember the naming protocol, right? So if you got angle A down here, side A is on the other side somewhere. So I'm going to make side A be 6 centimeters long, and I'm going to calculate the angle at B. All right, now here's what we got here. So I'm going to put a 6 centimeters down here, get my imaginary pencil out and draw a line. There it goes. I'll move my tools aside, and there I've got that, and I'll label it with a B. Now, that side length is 6. And we're set up for a sine rule calculation to find the angle at B because I've got angle A and side A. That's the side angle partnership that we've been speaking about in class quite a bit. The presence of that means you're going to be using the sine rule. And since I know the side length across from B, namely side B, I can go ahead and find the angle at B. And here's what happens when I try to do that. I solve that, and it tells me that the angle is 56.4 degrees. That's correct to 3SF, and I'll label that in there. And all of a sudden, this thing doesn't really pass the smell test. That angle actually appears to be obtuse, not acute. So what's up with the 56.4? So I'll get my protractor out and just measure. I try to make this really accurate, right? I know diagrams aren't necessarily drawn to scale, but if you actually draw them to scale, then they are. And I can see there that 56, that angle is not 56. In fact, what I further notice is that the angle outside the triangle over here is 56.4 degrees. So how do I reconcile that, and how do I alert myself to the fact that the other angle inside is not 56.4? Now you can tell that that baseline of the protractor is a straight, right? So you've got a 56.4 degrees occupying part of it. The obtuse angle on the other side is what we call the supplementary angle. That's the angle that adds to 56.4 to create a sum of 180 degrees. And since it's a straight line, it's 180. So it's 123.6 degrees in there, but my calculator didn't tell me that. It told me 56.4. How do I know that that's an issue? Obviously, finding 123.6 is not difficult because it's just a supplementary angle, but you got to know to do it. And what is that? Now, I just want to go ahead and complete the story here. If I was to get my tools back out and draw, this is what most people don't detect when they're starting off with this kind of trigonometry, is that 6 could have been drawn in that position as well. Now, since this is 6 and this is 6, that means you've got an isosceles triangle over here, this little guy. And that means the angles across from the two equal length sides are the same. They're both 56.4. And herein lies the heart of the ambiguity that we need to deal with. That 6 centimeter side length that sits across from angle A is sufficiently large to cause us uncertainty as to what the author was trying to convey when they told us the information, the partial information about the triangle. So we have to be on guard against that to make sure that we're not fooled. Not that they're trying to fool us, but we're not failing to come up with the fact that it could be taken more than one way. I think the best way of illustrating that is to draw a circle originating at this point here. Let's call it point C. And if you have a radius of a circle that's 6, you'll notice that you're going to pierce through this length over here in more than one place, meaning those two different radii, 6 there and 6 along here could both alternatively be the side length A across from angle A. So now let's see. And then, of course, I'm going to have the 123.6 down in there. And now it's a supplementary, but again, I need to know that it's something I need to look for. Now, I want to think about this circle. I've taken away side A and I've taken away point B. I just want to think about how big that circle could be that I need to actually consider there's more than one possibility here. Let's see. Well, 6 clearly was big enough. It could get larger. Notice that as it gets larger, in fact, the radius is now getting kind of close to 10. If it got bigger than 10, it would go off the end of point A. This radius of the circle would be quite large indeed, and I wouldn't have a triangle anymore down here. But I would still have a triangle going off in this distance here because no one said how long that big line there. So bigger than 10 is okay, but it removes the ambiguity. The angle would only be acute. If it was smaller, but I'm not sure how small, there could be 2 answers. Now, the time when we come back to there being only one answer is when the circle is tangent to the line. That means that the straight line that connects this dot over here to the circle and to the tangency is right angled. So we would have actually a right angle triangle. If we went any further, that circle is not even big enough to reach that line, and so therefore there is actually no such triangle that does that. And so the key lies in the 2 bits of information that were given there, the 30 and the 10. And I want to go back now and just examine the situation where we have the right angle triangle. This is the last case of it being only one non-ambiguous case. So if I was to find this side length over here, I could use SOHCAHTOA. Sine is opposite over hypotenuse, and I would come up with the fact that A would be 5. So if A is equal to 5, hence this number here, 10, times the sine of 30 degrees, then that's the smallest it could be that the triangle can actually exist. If it gets bigger than 5, then there's more than one case. But if it gets bigger than 10, it goes back down to one case, and it's purely obtuse. So I'm going to draw that as well here. If it gets bigger than 10, then you don't have this second case anymore because you've come flying off the end of the triangle to the left. So what do we have? We have a test now for whether or not an ambiguous case is to be considered. And it has to do with these 2 things I put in this little oval here, the 30 degrees and the 10. You can take a look at that. Yeah, you do have to examine these cases very carefully. And this is the situation when you have to think about it. If you've got a side length and a non-included angle over here. So we call this the SSA triangle. I'm going to move those letters. Don't look at them in the opposite direction. That's not very nice. So you have a side length that's given to you and another side length, and one of the angles is not included. So not this angle down here, one of the angles there, or potentially over here. Then you have to test whether or not the side that is across from the angle, how big is it in comparison to the side length that's adjacent to it times the sine of the angle. Now here, I'm going to go ahead and do this. Oh, by the way, going back and summarizing, if you have a triangle and the person stated it to you only conveying 3 angles, there's an infinite number of triangles, so that's not a problem we can solve. Obviously, you could look at a triangle with a magnifying glass and change its size, but it doesn't change the angles inside. If you've got 3 sides, this would be a cosine rule triangle. There's one unique triangle that has 3 known side lengths. If you have a contained angle, also a cosine rule question, you would have 1 unique triangle. And if you have a angle side angle or 2 angles on any one side, that is also a unique triangle. But now this is the one, the SSA, where it could be none, it could be 1, and it could be 2. And we need to have some sort of mechanism to judge which of the 3 we actually have. So here, I'm going to roll through the different cases and show you how this is going to work. This, I have a non-included angle. Angle A is 10 degrees, and it sits across from side A, obviously, and B is another side. So we've got an SSA. We don't have angle C. That would be an included angle between sides A and B. So what I'm going to do is I'm going to deliberately draw just about the most non-to-scale diagram I can. I'm going to make something that looks really quite isosceles, and there's no way that 9 and 3 are relatively accurate to each other, right? The 3 is far shorter than 9, but I've not drawn them that way because I don't want to get caught up in what it looks like. I just want to deal with the consequences of the information that are stated to me. So what I do is I take the side and the angle that are nearest to each other, the 9 and the 10 degrees, and I multiply 9 times the sine of 10 degrees, because that would tell us how high this length is here. And then I can gauge what's happening with the 3 in relation to it. So I end up with a test value of 1.56. That's when 9, the adjacent side to the angle, is multiplied by the sine of that angle, and it creates a value. And that value is critical for us in determining where we go next. Now, what I do is I imagine both the 9 and the 1.56, and where they reside on a number line. And when I do that, I got to just judge, where does 3 slot in? Does it slot in here, less than 1.56? Does it slot in here, between 1.56 and 9? Or does it slot in here, bigger than 9? Well, 3 clearly is right in this zone over here. And here's the ambiguous case consequences. If the number that's across is smaller than 1.56, there is no such triangle that we can work with that does this. If it's between the two numbers, 1.56, the test value, and the adjacent side length here, 9, then there are 2 cases and we have to consider them both. If it's bigger than 9, then there's just one case. So since in this case 3 is between 1.56 and 9, there's 2 separate cases, and I'm going to now adjust my diagram to show you what they actually look like. So you could have the triangle that's the large obtuse one here, or you could have this other kind of weird oblique, also obtuse because it's an angle over here. But notice that in both cases 3 sits across from the 10 degrees, and this is a non-included angle of 10 degrees, and the ones that we have to check whether or not there's more than one case. So if I go ahead and do my sine rule, I can see that the angle is 31.4 degrees, which of course is this one over here. But now that I know that we're in a 2-case situation, I also take the supplementary to that, and that's what I've done here. I've gone 180 minus the previous answer, and it's 148.6. So if I was to annotate my diagram with that, I would know that I've got 2 situations here. That doesn't mean there are 2 triangles. It means the way the information was stated to us, it was ambiguous. It was unclear. We're not sure that it was one or the other. So we have to consider both until we've got some other way of saying it's not that. Okay, here we go. Another one. Again, do this exact same thing. I'm going to draw a deliberately to scale diagram. I've got the 6 sitting across from the 40, and I've got 5 adjacent to the 40. So we have a non-included angle here for that the 40 degrees is not included, and 6 sits across from it. So if I want to find angle B, I'm going to have to use the sine rule. I'm going to take my test value, which is 3.21, and I'm going to picture it and say, well, 6 is actually, consider 3.21 as my test value and 5 is the adjacent one. 6 is bigger than the 5. That means there's one case again, and you definitely have this long one here. So B is exactly what your calculator will tell you it is. It's an acute angle, and that will be 32.4 degrees. And there can only be one case. If you were to draw another one with 6, I don't know where you'd put it. I get it back over here somewhere, but it would be, the 40 wouldn't be in the triangle any longer. One more. We've got an angle of 35 degrees sitting across from a 2, and we got a 5 adjacent to it. So again, the deliberately non-drawn to scale triangle. I'm going to go ahead and just figure that out. The test value comes from taking sine times sine of 35 times 5, and that's 2.86. So if I were to critically look at where does this opposite side here, 2, sit in relation to 2.86 and 5, I would get it's less than 2.86. So there's actually, this triangle can't exist. As it's stated by the author of the question at the top of the screen, it can't exist. And just to verify that point, if I was to try and draw that, this is exactly what it's going to look like. The 2, if you could imagine like a rope hanging from the end of a 5-meter ladder that was somehow suspended at a 35-degree angle, it wouldn't even reach the ground. There can be no triangle. It's not long enough to close the gap from the end of the 5 to get down to this line down here. So there's no angle at all that can do that. Okay, so let's see, where do we go now? Off to the textbook. We've got some exercises due in exercise 11G. 1, 2, 3, 4, 5. Don't ignore them. We got to get them done. We got to be able to draw the diagram and test whether or not we've got an ambiguous case. Now, obviously, that's going to show up quite a bit in this section because that's what this section is about. But later on, we're also going to be given questions where they're not tipping their hand. You're not being told. You'll have to discover it for yourself whether or not we have the situation. Okay, good luck.